This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're diving into the fascinating world of ocean tides, a topic that's both scientifically complex and surprisingly relatable. We'll be exploring the physics behind these rhythmic rises and falls of the sea.
Indeed. It's a topic that often seems simple at first glance, but the underlying mechanics are quite intricate and involve a delicate interplay of gravitational forces.
Exactly. Many people are familiar with the moon's role, but the details are often overlooked. For instance, did you know there are actually 2 high tides a day?
That's right, and the reason for that isn't immediately obvious. It's not just a simple pull from the moon on one side of the Earth.
That's what makes it interesting. Let's unpack the science behind this cosmic ballet, as the article so eloquently puts it. Let's start with the fundamental concept, tidal forces. Can you explain how these differ from simple gravitational attraction?
Certainly. While gravity is the underlying force, tidal forces are about the difference in gravitational pull across an object. The moon's gravity is stronger on the side of Earth closest to it and weaker on the far side. This difference in gravitational pull is what stretches the Earth, creating the tidal bulges. It's not just a simple pull, it's a differential force.
So it's the unevenness of the gravitational pull that's key. This leads to the 2 tidal bulges, one facing the moon and one on the opposite side.
Precisely. The bulge on the near side is intuitive. The moon pulls the water towards it. The bulge on the far side is a bit more subtle. It's due to inertia. The Earth is pulled towards the moon more strongly than the water on the far side, creating a relative bulge there.
The article also highlights the sun's role despite its greater distance. How significant is the sun's contribution to tides?
While the sun's mass is far greater than the moon's, its distance significantly reduces its tidal effect. The tidal force is inversely proportional to the cube of the distance. This means a small change in distance has a dramatic effect on the tidal force. The sun's tidal effect is roughly half that of the moon's.
That's counterintuitive to many. They assume the larger mass will automatically mean a stronger tidal effect.
Exactly. It's a common misconception. Distance is the dominant factor in determining the strength of tidal forces.
This leads us to spring and neap tides. Can you explain the astronomical alignments that cause these different tidal ranges?
Spring tides occur when the sun, earth, and moon are aligned during new and full moons. The gravitational forces of the sun and moon combine, resulting in larger tidal ranges. Neap tides, on the other hand, occur when the sun and moon are at right angles to each other during the first and third quarter moon phases. The sun's gravity partially cancels out the moon's, leading to smaller tidal ranges.
So it's a matter of constructive and destructive interference in gravitational forces. The article mentions that tidal forces don't just affect the oceans, they also flex the Earth itself. How significant is this effect?
It's a less obvious but still measurable effect. The solid Earth is deformed by tidal forces, albeit to a smaller extent than the oceans. Estimates suggest that rocks stretch by about 30 centimeters daily due to these forces.
That's remarkable. It's a testament to the power of these seemingly subtle forces. Another fascinating point is the moon's gradual recession from Earth. How does this relate to tidal energy transfer?
The tidal interaction between the Earth and the moon transfers energy from Earth's rotation to the moon's orbit. This causes the moon to slowly spiral outwards, receding from Earth at a rate of about 3.8 centimeters per year. Conversely, Earth's rotation is gradually slowing down.
So the moon's distance from Earth isn't constant, it's slowly increasing over time. Let's talk about the practical applications of understanding tides. The article mentions surfing, climate science, and space exploration. Can you elaborate?
Absolutely. Accurate tide predictions are crucial for surfers and sailors. In climate science, tidal mixing influences ocean currents and global climate patterns. In space exploration, tidal forces play a significant role in the dynamics of celestial bodies, influencing the formation and evolution of planetary systems. For example, tidal forces can rip apart asteroids and power subsurface oceans on icy moons.
The impact of tides extends far beyond the simple rise and fall of ocean waters. The article emphasizes the inverse cube law. Can you explain its significance in understanding tidal phenomena?
The inverse cube law states that the tidal force is inversely proportional to the cube of the distance between the celestial bodies. This highlights the extreme sensitivity of tides to distance variations. Even small changes in distance can lead to significant changes in the magnitude of tidal forces.
This explains why the moon, despite its smaller mass, has a greater tidal influence than the sun. The article promotes the use of an interactive simulation to enhance understanding. How valuable is such a tool in learning about tides?
Interactive simulations are invaluable. They allow users to visualize the complex interplay of gravitational forces and observe the resulting tidal patterns in a dynamic way. Features like pausing, dragging celestial bodies, and adjusting speeds allow for a deeper understanding of the concepts.
It transforms a potentially abstract topic into a tangible and engaging learning experience. The article includes a quiz and essay questions. What are the benefits of such assessment methods?
Quizzes provide a quick assessment of comprehension of key concepts. Essay questions encourage deeper thinking and application of knowledge. They allow students to demonstrate their understanding of the underlying principles and their ability to connect different aspects of the topic.
A combination of both methods provides a comprehensive evaluation of learning. The article also includes a glossary of key terms. How important is it to define and understand these terms precisely?
Precise definitions are crucial for clear communication and understanding. The glossary ensures that everyone is on the same page regarding the terminology used in discussing tidal phenomena. Misunderstandings of these terms can lead to confusion and misinterpretations of the underlying physics.
It's essential to establish a common vocabulary for effective communication. The article discusses the viral potential of the content. What elements contribute to its shareability and engagement?
The article's success in terms of shareability stems from its blend of scientific rigor and engaging storytelling. The use of relatable hooks, interactive elements, surprising facts, and visual appeal all contribute to its potential for widespread dissemination. It transforms a complex scientific topic into a captivating narrative.
It's a great example of how to make complex science accessible and engaging for a wider audience. So in essence, understanding tides involves grafting the interplay of gravitational forces, the inverse cube law, and the dynamic response of both the oceans and the Earth itself.
Precisely. It's a fascinating interplay of forces that shapes our coastlines, influences our climate, and even plays a role in space exploration.
That was a great discussion. Thank you for sharing your expertise.